Okay, hello class. How are you guys doing? We are now in week 9, I believe. Yes, week 9, which is Subsidence and Soils. So this is a really cool chapter. Subsidence or subsidence, you might have heard it be called. I call it subsidence, but anyways, it's the same thing. Is one of those natural hazards that is not very spoken of, and you don't hear too much about it, but that is happening all the time, and one that a lot of money has been spent into, and we don't realize it necessarily right away because usually there is no large amount of lives lost, within one single event. This is kind of a long-lasting event for the most part. In fact, I bet you that your backyard is probably seeing some subsidence as we speak. In fact, I'm sure that mine is. So this is one of those really cool natural hazards, or I think so. I'm pretty sure most geologists would agree with me. So pay attention during lecture and have fun. So we're going to start this chapter by going into what soil is and a few characteristics of soil before we get into actual subsidence and what natural hazard that is and what is going to have to do with humans and how we can mitigate it. So we'll start with soil first. So you may think that soil can just be dirt, but there are many different definitions from different types of scientists about what soil really is. So soil to an engineer, for example, is any solid earth material that can be removed without blasting. Soil for a soil scientist or even a geologist is going to be solid earth material that has been altered such that it can support rooted plant life. So if you think about those two definitions and you look at the image below on this slide, do you think that both a soil scientist or geologist or an engineer would agree that what that guy is holding in his hands is soil? I probably think that they would in this case, but there are many cases where they don't agree. And so for contractors' jobs, this becomes a difficult thing to decipher. See who was doing the study of that specific soil and what they said about it is going to have a big effect on what they do. So in addition to, simply the study of soils and what kind of hazards it can cause, it also helps us evaluate many of the natural hazards that we have seen already in the semester and some that we have yet to see. So as you're seeing, this picture below is kind of blurry. I apologize for that. But you're seeing some buried soil underneath, and then you're seeing some sands and silts that are covering easily, what is that, like 4 inches or so. And they are telling us right there that those are tsunami sands. They're sands that were deposited by a tsunami. So because of the nature of the sands, that are sands and silts and clays mixed together, and they're in such a high amount deposited at one single time, it tells us that it must have been some sort of catastrophic event that deposited them. So the soils actually tell us a lot about different hazards that have happened in the area where we find them. So if you can think of a few of the natural hazards we've already covered, I'll give you a couple of seconds. Think about it. So if you think that soils could be deformed by earthquakes, you bet. By volcanoes, for sure. By mass wasting events, you bet. What else can you think of? Here in the state of Idaho, by wildfires, largely. By flooding, definitely. And then by other severe weather and kind of atmospheric processes that we'll cover in the next few chapters. All these soils are deformed, and so again, the study of soils doesn't just aid us in determining what specific hazards it has to humans, but it can also help us evaluate the natural hazards that it has seen, if you would, that it has witnessed, and it's been exposed to in the past. Okay, so soil itself is going to be composed out of roughly, and then again this varies from place to place, but it's going to be composed out of roughly 45% is going to be earth material, so it's going to be rock eroded sediment. About 5% of it is going to be organic material, or humus in this case. Or not humus, I don't know how you would say it. I think it's humus. 25% would be water, and then 25% would be air particles. So the soil itself is not compacted, it's not cemented like rock, so it's gonna have a lot of air within it, as well as water that is flowing through some of those air spaces, right? So 50% of the soil as we know it is, empty or not full of earth particles. The rest of it, for the most part, is earth particles, but a little bit is organics, okay? So the main eroded particles, or the biggest chunk from the soil, the 45%, comes from the weathering of rocks. So all those eroded particles come from weathering. So weathering is going to be the process of breaking down rocks. There's two types of weathering, or two main types of weathering. There's going to be physical weathering, and then there's going to be chemical weathering. The picture on the bottom right shows you a type of physical weathering. So this type of physical weathering is called frost wedging, and I talked about it a little bit in the last lecture, in the mass wasting lecture. So again, what happens is that whenever you have a smaller crack within the rock, because it's a point of weakness, water will intrude into that crack, and then once temperatures get below 0 Celsius, then the water will transform into ice, and as it does so, it will expand, because ice is going to be less dense overall than water. So it's going to expand, and as it expands, it's breaking up that rock even further, and then once the temperature gets back up, it will thaw, and it will leave the crack that is now bigger. And so if that cycle continues on year after year, you're going to get the breaking up of that rock, and not just each crack, but also smaller particles near the crack are going to basically fall off the rock. So that's how the frost wedging in this picture is working. The picture on the top right is an example of chemical weathering. So in this case, the specific type of chemical weathering we're seeing is called dissolution. And how that happens is you have carbonic acid rain, basically, that combines with the carbon we have in the atmosphere, and that is going to come down and erode chemically. So it's going to, all the elements within that rain are going to react with the elements that are found in the rock, and they're going to dissolve, basically, pieces of the rock, the top surface that the water has access to in that rock. So dissolution is very strong in certain types of rocks, and it's usually rocks that have or are made up of elements that can react with this acid rain. So limestone and marble, which contain calcium carbonate, usually tend to be very easily chemically weathered. So that is what we're seeing there on that picture on the right, is going to be some limestone getting dissolved. And then on the bottom left picture, what you're seeing is organic matter that is decaying slowly. So although the soil officially contains live organic matter, and by that I mean roots that may be living, the very great majority of organic matter that the soil contains is going to be dead organic matter, so matter that is decaying constantly. And the largest percentage of that dead organic matter comes from plants rather than fungi or animals for the most part. Okay? So again, the percentages that make up soil are 45% is going to be particles, sediment particles, 5% is going to be organic matter, 25 water, and 25 air. And again, that's an average of pretty much soils worldwide. The soil development itself is going to depend on these 5 things, and I'm not going to go into depth with them or on them, but if you're curious about them, definitely let me know, and I will more than happily clarify for you how it is that these 5 things influence the soil development. So those 5 things are going to be climate, and probably climate is the most important one of those. Climate is going to be temperature and moisture combined, okay? And then we have topography being as one of those things. The parent material is going to matter greatly, meaning what is the main source of the sediments that the soil is composed of. Time is going to be very important, and also the organic processes that happen on top of that area where the soil forms. Those are going to be the main 5 things that the soil development depends on. And then this little cartoon here shows you the different soil horizons, okay? So these layers are called horizons. So the first soil horizon, and again, I should clarify, these soil horizons don't always appear in every place where you have soil. So I may have the O horizon and the C horizon, but I may not have any of the horizons in between them. Or I may have all of them, but not at the same thickness. So it varies from place to place, but these are the main few horizons that they've discovered to appear in a soil sequence. So the first horizon going from the surface towards the depth of the earth are going to be the O horizon, which is the organic horizon, hence the O. The A horizon, which is going to be composed mostly out of still organics, but not nearly as much as the O horizon. I think it only has about 30 to 40% organics, and then the rest is going to be pore spaces, water, and then some of the particulate matters from the sediment. The E horizon, which is called E horizon because it's the zone of alluviation or zone of leaching. So that is pretty much where you're going to get the most amount of leaching from the water that is percolating through the soil, that is infiltrating and staying within that soil horizons. So alluviation is happening at E. The water is coming in and leaching all the minerals from E down towards depth. Then the B horizon is going to be the zone of accumulation. So all of those materials that have been leached from E are going to end up at B, at the B horizon, where you get accumulation. Many a times you get in between B and C, you get this layer of hardpan, which is pretty much all of those accumulated minerals pretty much cement together and cause kind of like this really hard layer that doesn't let you get any deeper, but yet you have still soil underneath. So water won't get any deeper than that hardpan layer because of the hardpan itself, because it's creating that nice compacted layer of minerals that are not cemented. But when you don't have a hardpan, which is in most cases, you're going to get the C horizon underneath the B horizon. So the C horizon is otherwise called the regolith, or for the most part is composed out of regolith. Regolith is going to be weathered material from the parent material. So it's going to be mostly, like pretty much 100% just particulates from the parent material that are now loose and not consolidated within the parent material. So that is what C is, mostly just those particulates. And then below C, you're going to have your parent material, meaning the material where most of those sediments are going to come from. If you're thinking that many a times you get soil that does not, or it's in a place where the parent material is not, meaning maybe your parent material is granite, but the soil on top is made out of, let's call it shales, then that may be because the parent material is from another source. Maybe those shales particles were transported through a medium and now ended up on top of that specific parent material. That can happen very often, but yet we still name the soil horizons as they are laid out in front of you right now.